Now let's look at how all of these forces acting must balance. We have Fa, the force that support A applies upwards on the beam. Fb, the force that support B applies upwards on the beam. W1, the weight force of the beam itself. Being a 30 kilogram mass, it will have a weight of 30 times 10 or 300 newtons. And the weight force of the person on the beam, W2. Being a 50 kilogram mass, this person will apply a 50 times 10 or 500 newton force to the beam. Now the concepts here are quite simple. All the forces must balance, and this means three things. 1. Vertically, the upwards forces, Fa and Fb, must balance the downwards forces, W1 and W2. 2. Horizontally, any forces must also balance. Since we do not have any horizontal forces, that equation does not apply here. And thirdly, and importantly, the rotational forces must balance about any chosen point of rotation. And for this question, although it doesn't make a lot of difference, we're going to choose point A as our point of rotation, shown here by the purple dot. We could have equally chosen point B, or even the centre. A point worth noting is that if we choose our point of rotation below one of the forces that we're required to work out, Fa or Fb being the unknowns, then the equations work out more easily because those unknowns do not both appear in the second equation. More about this in a moment. So for now, we'll just remember to choose our point of rotation below or above one of the unknown forces. In this case, support A. Coming back to our first equation now. Shown here at the bottom of the screen, total upwards forces must equal total downwards forces. And again, we've written that as an equation. Fa and Fb must equal W1 and W2. Now we know we can calculate W1 and 2 by simply multiplying their masses by the gravitational field strength, which is approximated to 10 on the Earth's surface, 9.8 being the more accurate value, but 10 being the exam value. So 30 times 10 substitutes in for weight 1, which is 300 newtons, and 50 times 10 for weight 2, which is 500 newtons, for a total of 800 newtons. Now notice this equation has two unknowns, Fa and Fb, and cannot be solved with a unique solution at this stage. So typically what we do is we label it as equation 1 and recognize that it may be useful later on. Let's now move on to our second concept, and that is the idea of rotational forces balancing. So we say total clockwise, or should I say total anti-clockwise rotational forces or torques must balance the total clockwise rotational forces about our point A, shown as the purple dot here. Now if this weren't the case, the object would start rotating, which it isn't, and therefore they must balance. Now keep in mind that torque is calculated as force by distance from the point of rotation. Let's identify which of these forces has a clockwise rotating effect and which ones have an anti-clockwise effect. We'll start with the anti-clockwise. Point A is our point of rotation. If this were free to rotate about point A, then the forces upwards on the right, in this case Fb, would start to cause a rotation in an anti-clockwise sense. So Fb contributes an anti-clockwise torque. W1, however, pushes downwards, which would contribute a clockwise torque. And likewise, W2 pushing downwards would start to create a clockwise rotation about point A, if it were the only force acting. Interestingly, Fa doesn't contribute any rotation because it's acting right at that point. It has to be acting at some distance. The distance here is 0, so is the torque. And you know from your own experience that pushing directly on an object doesn't cause it to rotate. You have to rotate it from a distance, apply a force from a distance to that point of rotation to create any rotating effect. So, our anti-clockwise torque in this case is just provided by force B times the distance from force B to our point of rotation. Now it's not directly shown as a distance on our diagram, but we can infer it from the distances given. The distance between the two supports in this case would be 6 meters. Take away 1.5, take away another half, so that would be a distance of 4 meters from our point of rotation. Now we will consider the second equation, that is the idea that rotational forces must balance. We've chosen our point of rotation, point A, as the point below or above, in this case, support A, below where I've shown force A. Now before we can apply this concept that the total clockwise and anti-clockwise rotations about point A must balance, we first must decide which of the 4 forces contributes to an anti-clockwise rotational effect or torque, and which of the 4 forces contributes to a clockwise rotational effect. So let's go through them one at a time. Force B, acting upwards on the beam, to the right of point A, if it were the only force acting, it would start to move the plank or board upwards. This would start to create, as shown by my mouse cursor moving, a clockwise, should I say an anti-clockwise rotational effect. So FB contributes an anti-clockwise torque. W1, however, is pushing in the opposite direction, downwards. If it were the only force acting, the board or the beam would start to move downwards and in a clockwise sense about point A. So W1 contributes a clockwise rotational torque. Likewise, so does W2, pushing downwards creates a clockwise rotation. Now, interestingly, the force acting upwards at support A, labelled FA, is acting right on point A, and therefore contributes no rotation about the point, since the distance is 0. You know from your own experience, if you push directly on something it doesn't create rotation. You have to push slightly to the side of the point at which it rotates to create a rotation. So FA does not appear in the equation. As I mentioned earlier, this simplifies the mathematics. So let's look at the maths. Total anti-clockwise torque in this case is just provided by FB, being the force FB times the distance from FB to the point of rotation. That distance is not directly shown, but we can infer it from the diagram. It's the 6 meter length, take away 1.5 from one end and half from the other, is remaining length of 4 meters between the two supports. So the anti-clockwise torque here is represented by FB times 4. On the other side, the total clockwise torque is provided by 2 forces. W1 times its distance from support A, W1 being halfway along is 3 meters from the end, take away 1/2 of a meter from the end, leaves a distance of 2.5 meters from point A to W1. So in this case, the torque provided by W1 in a clockwise sense is W1 times 2.5, plus, for the total, plus W2 times its distance. Now we're told that's 2 meters from the end, so that's going to be 1.5 meters. W2 times 1.5. From here, the mathematics is as it was before. The weight force is the mass times gravitational field strength in each instance. So 30 times 10 and 50 times 10 times the respective distances, both contributing coincidentally to 750 units of torque. The units of torque are newtons times the distance meters, newton meters. So that's a total of 1500 newton meters clockwise. We don't know FB, but we can now solve it by dividing both sides by 4 to see that force B must be 375 newtons acting upwards. And this is where we can now refer back to equation 1, which told us that the 2 forces, FA and FB, must total to 800. We now know that FB is 375, so we substituted into equation 1 to say that FA plus, I don't know what this is, but we'll change it, 375 must equal 800, and therefore FA must be 425 newtons. And as predicted, slightly bigger than FB because the person is standing close to that support. And that's how we use the concept of rotational forces in balance to calculate unknowns when just equating upwards equal downwards forces doesn't provide us enough information. There's no limit to how many forces we can solve for in this type of situation. By choosing rotational points at various positions, we can get any number of equations that we require to solve for the unknowns as we go through the question. Generally speaking, however, there are only 2 in Year 12. The same process can be applied to lots of different situations, not just a beam. As we will see in the next question, we have a person on a diving board, and a little later on, someone pushing downwards on a remote control, and situations where we have beams supported by cables. All of these can be calculated based on the same concepts, which will be the focus of our next lesson. Probably a good thing to do now is to go to problem sheet 21, which has questions on supported beams. I will go to that now and show you where that is. Okay, this is problem sheet 21, equilibrium of horizontal beams, and as you can see there are a range of questions, and in each case the answers are provided on the back of the sheet. Your first step in each of these questions is to draw a diagram that is consistent with the question. In this case, question 1, I'll help you get started. A horizontal beam of mass 10 kilograms and length 4 meters is supported 0.5 meters from each end. So very similar to the last question we did. Draw a diagram, find the size of the force provided by each support. A slightly simpler version to get you started. You should attempt these for homework. You won't be able to do all of them properly, but you'll be in a position then to understand what we go over with beginning of next lesson. Thanks for your time. I'll look forward to seeing you next time. Mr. Phillips out.